Hey, this is a video for 4.3, Soil Composition and Properties. So go ahead and check out the overview and set up your guided notes. So when we're considering soil, recall that there are mineral components to the soil, and we can classify these or divide them into three categories, and we can separate them by size. So the largest particle that is present in the soil is sand. And you've been to a beach, or if you've been to a beach, you know that sand is a very fine particle. But when we're considering soil, it's actually the largest of the three particle sizes. So in fact, if I'm doing this by scale, the sand is too big that it can't even fit on this screen. Now, sand is good for promoting drainage. So because the particles are so large, there's going to be a lot of spaces in between them. So that will allow water to flow between the particles. It will also limit the compaction of the soil because these particles are so large, they cannot get close to each other or as close to each other. So it will prevent the soil from becoming too compacted. And we want to have these spaces in between the particles because we want water and oxygen and other solutions to travel between them. We have silt, which is the medium size. Silt is just kind of all around average size. It will promote water circulation, or water retention, and air circulation. We want water to be held to these particles because we want it to be available for plants. And also there are nutrients that are attached to the water. So we want these nutrients to also be available to the plants. But we also need air circulation. There's going to be gases exchanged in the soil between the roots and the environment, but also there's going to be microorganisms living in the soil that will need access to oxygen and to get rid of carbon dioxide. Now, clay is the smallest particle. Clay is so small. We're going to be working with this in class, but we really can't see clay with our naked eyes. It literally just looks like cloudy particles, like cloudy water. But the particles in clay have a negative charge. So what that means is they're going to hold on to some ions. They're going to attract as well the water molecules because recall that water is polar. So the areas of the clay that are negatively charged are going to be attracted to the positively charged hydrogen atoms. And along with that, it's going to attract some of these cations that are valuable nutrients. Calcium, for example, magnesium, potassium. These are all positively charged atoms. We'll also attract some heavy metals that are not necessarily that could be toxic to organisms, but we'll talk about that in future lessons. Now, there's also this cation exchange capacity, which is the ability of soils to exchange these cations with the external environment. So these, when you have a lot of clay, it will increase the cation exchange capacity, just like it's affecting the ability to hold water. Along with the water, because of the polarity of the water, we are going to be attracting particular nutrients. So soil with high amounts of clay will have better cation exchange capacity. Too much clay and it may hold on to these particles too strongly. Not enough clay and these cations will not be available for the plants. Now, we have to consider porosity and permeability. So we have two samples here. The top sample could represent silt or clay. The bottom sample could represent soil, for example. Now, porosity is measuring the space in the pores, the pore space. In other words, it's measuring the amount of blue in these diagrams. So the blue represents water, or could represent water. But when you have this open space, it's actually a ratio. So there's no unit that you're going to be using. So you're going to be measuring the open space versus the overall volume or the volume of the particles. Porosity and permeability are related to an extent, but they do not mean the same thing. Porosity, we're just measuring the open space. There's actually more porosity in sample A, because you can see there's more blue, There's actually less porosity in sample B, but the spaces in there are larger, so there will be a better flow of water. If you had something like clay with a lot of spaces between the particles, that's also going to hold on to the water, and the water is going to be held very strongly because of the difference in charges. Remember that clay is negatively charged. Now, permeability measures the flow of the water. So you can do, when we measure permeability, we can measure it by the amount of time or the amount of volume of water that goes through. Usually it's the volume of water per unit of time. And sands are going to have high permeability, and clays are going to have very, very, very low permeability. In fact, we use clay soils to line we could line, a pool. You could line a landfill to prevent the leakage of the liquids from both items. Now, when we're measuring the soil texture, we are going to be determining the amount of sand, silt, and clay, and this can be done physically, where you're going to be using a ratio. You take a sample of soil, and you want to eliminate as much of the organic material, as many of the rocks as possible. And you're going to put it in water with some sort of maybe a detergent or something that's going to help the particles stick to each other and settle out faster. But the sand is going to settle first because it is the largest, then the silt, and then the clay. The sand will settle out in a matter of, a minute. Silt will settle out maybe within an hour, and clay will take over a day. Some clay samples will take a few days. We may leave them over the weekend in order to settle out if we do this in class. Now, it's best to have something that is relatively square on the bottom, because if it's rounded, you're really kind of not measuring accurately. Now, what you will do is you're going to be using this percent calculation. The percent over 100 equals part over the whole. So what you're going to do is measure the amount of total sample that you have, and then you're going to measure the component of each one. So for this example, the whole would be the clay. At the top of the clay, once this is all settled out. This water will become very clear. Again, when you're doing this activity, you put the soil in there, you shake it up for a few minutes, get it nice and distributed, and then allow it to settle. And the whatever value is on the top is going to be your whole value. And then you're going to measure each individual part. Like, for example, this would be the clay. This was 4 centimeters, for example. So this would be your equation. So you have x over 100 equals 4 over 20. You're going to solve for x, cross multiply and divide. 20% of your sample is made up of clay. Now the next one, the silt, is 8 centimeters, and it's not 8 centimeters from the bottom. We're literally measuring from here to here. That is 8 centimeters. The entire volume was 20 again. So that won't change. And if you notice, the sand is also the same, has the same height in this sample as well. So both of them are 8 is the part, and the whole is 20. So you would set it up like this. And this, since 8 is twice as much as 4, you can kind of predict it's going to be 40%. So we have 20, 40, and 40. So now what we do is we will look at a soil texture triangle. And a soil texture triangle looks something like this. And you're going to have the percent clay, the percent silt, and the percent sand. So we're going to start with the clay, which is 20%. And I always tell my students to use this as think of this as a graph. And this would be the y-axis, for example. And then just draw straight across. So you're going to find the 20 on there. And then you're going to draw a line straight across, and then you're going to move it and draw your lines. So this is going through to show you using the soil texture triangle. This is just a little GIF that I made. You can observe that, and this is how you would do it. You do 20% clay, and that one is the sand, I believe, and that one is the silt, and where they all meet, that sample right there is loam. So you will have access to a soil texture triangle. If you ever have to do this on a test, you will be provided with a soil texture triangle. So loam is the absolute best soil for agriculture. It has just enough water holding capacity, just enough cation exchange capacity, great amount of drainage, and the amount of pore space is adequate as well. So this is the best soil for agriculture. Where I'm from, I hope that I was able to I went home and got some soil samples. Hopefully I can bring back some loam. The soil of my parents' yard is actually sandy loam, which is good, but it's not as good as loam. There again is enough sand, so you're going to have some drainage. There's going to be enough clay in order for the cation exchange capacity. Now, the soil fertility. What we want in the soil to make it fertile is we want these nutrients. We want nitrogen, potassium, phosphorus. Nitrogen, phosphorus, potassium, magnesium, calcium, sodium are all nutrients that are necessary for plant growth. These NPKs are the major ones. And if you ever get like Miracle-Gro or any sort of plant fertilizer, it's going to give you NPK values. Now we also want soil to hold water, but not too much. If it has too much clay, it's going to hold too much water. So factors that are going to increase the amounts of nutrients could be organic matter. If you have like digested or decomposed leaves and humus, decomposers will also increase the nutrient capacity, like if worms are defecating in there. The soil texture, again, more clay is going to hold more nutrients. And also the pH. So when it is too acidic, there's going to be hydrogen ions present in the soil, and they're going to bind to the clay particles, so the clay will not be able to hold on to these cations. Now, water, factors that are going to increase water holding capacity are going to be soil aeration. If air can get into the soil, then water can get in. Organic matter, because that will also attract the water to the organic material. Again, the soil texture. Sand will allow more water to flow through it, and clay will hold on to more water. And then the root structure. So if the roots are penetrating the soil, that can also help to aerate the soil, make little air pockets in there that water can get in. Now, factors that are going to decrease the nutrient holding capacity. If we have a low soil pH, like I said, if we have excessive rain, it may wash away key components to the soil. If we have unsustainable agriculture, we keep planting the same crops over and over and over again, it is going to remove the same nutrients. And finally, soil erosion will remove the nutrients as well as the soil particles. Now, factors that are decreasing the water in the soil. Soil compaction. If the soil is compacted, there's less pore space in between the particles. And if there's less pore space, less water can get in. Erosion will also decrease the water holding capacity, because if there's no topsoil, there's no soil particles that can hold on to that water. Again, soil texture. Too much sand is going to decrease the water in the soil, because the water will not be held strongly to the soil particles. And also, if the roots are dead, if you pull up roots, if you have deforestation, if you have overgrazing and all of the grasses are eaten, there will be no roots. That will not allow the plants to hold water. Remember that plants act as staplers and sponges. They staple, they hold the soil in place, and they absorb water from the soil. Now, there are some soil quality tests that we can conduct. The soil texture, you're going to, like I said, put the soil in the water, shake it up, allow it to settle. You can determine the amount of, the percent of the composition of each one of the particles, and that can give you information on the quality of that soil. You can also measure the permeability. You can pour water in a sample of soil and measure the amount of time that it takes to drain through. This will give you the, if you also have the components, like how much sand, silt, and clay is present in the soil, this can also indicate the permeability. The pH, you can use pH strips or a pH meter, and that will also tell you if the soil is acidic. It will very likely hold fewer nutrients. The soil color. You can compare the color of the soil. Certain components that are in the soil will have specific nutrients. If it's a rusty colored soil, it might have a large amount of iron, and that can indicate something about the soil quality. It can also indicate the water or the nutrient holding capacity. You can also measure the amounts of nitrogen, phosphorus, potassium, any of the nutrients. It can indicate if there is a lot of nitrogen compounds, there can be high levels of productivity, even potentially eutrophication, if it is near a body of water. So I just gave you a bunch of information. I would like you to respond to this check for understanding. And now for our FRQ practice, I want you to describe a method to increase the soil's water holding capacity. I hope that this video was informative. I thank you for your attention, and I will see you soon.